All right. Electrolysis, as we have explained earlier, electro comes from electricity, right? And lysis is a word that is commonly used in biology and chemistry, and it means breakdown. So, to be honest, if you remember types of reactions, when we decompose something with the help of electricity, that is known as electrolysis. So electrolysis is actually breakdown of substances using electricity. Now, electricity has a phenomenon known as conduction. Things can be conductors or can be insulators in terms of solids. We call a solid conductor if it can conduct electricity. Otherwise, if it can't, we call it an insulator. There is a huge table of conductors and insulators in front of you from different examples. You know that all the metals, copper, silver, aluminum, are good conductors. Even alloys such as steel and brass are good conductors. And the only non-metal on the planet that is a good conductor is carbon in the form of graphite. Rest all giant molecular substances, even sand, silica, all in the list, cannot conduct electricity. Even simple molecular ions such as sulfur and iodine cannot conduct electricity. We call them insulators, or we may also call them non-conductors. Remember, this word only applies to solids, right? So, moving on, electrical conductors are actually real beneficial substances for us. These are the substances, they conduct electricity, and they do not chemically change in the process. Supplying electricity is something that has been a part of IGCSE papers way too many times. Now, we do understand we supply electricity using power cables. The domestic cables that we use at our homes are made out of copper. Why? Because copper is a very good electrical conductor. It has very high electrical conductivity, which means it's very efficient in conducting electricity. However, overhead power cables, the high voltage power cables, are not made out of copper. They're made with the help of aluminum. Aluminum is also a very good conductor, but at the same time, other properties of aluminum, why it is preferred over copper, is that it has a low density, and that prevents sagging. Now, what is sagging? We are talking about overhead power cables, which are based on towers, and the cables are usually connected from a tower to another tower. I hope you understand that in harsh summers, the metals expand, and when they do, they start sagging like this. They drool. Drooling is also known as sagging in science. Since it has a low density, there is very less sagging in aluminum, which is actually pretty safe for us. On the other hand, apart from being a good conductor, low density, less sagging, it is resistant to corrosion, does not corrode. And cables are also strengthened with a steel core. To understand this, strengthening with a steel core or insulation with a plastic or a ceramic material, we need to understand the whole thing with the help of a diagram. Let's move on to the next page. Let's understand the whole diagram. So the power cable has a central part, we call it a core, and it is made out of steel. This is for support because aluminum is too low in density. Steel core is going to provide its support. Then aluminum has actually a good conductivity. That's the reason why we use it, right? And afterwards, this is filled with, I actually shouldn't be saying filled, actually covered with insulating material, plastic, right? Why do we put plastic over there? As plastic is an insulator, so it would keep us safe. If accidentally you touch the wire, you're not going to get electrocuted. So plastic being the insulator keep us safe. Not just that, we have been talking about ceramic. Now, in case of ceramics are actually for the connection. We commonly call them pylons. That's how the wires are connected to these. So if even if they start drooling, Even if they contract during harsh winters or expand during harsh summers, they won't break off from the tower. That's why pylons are there. So all of this electricity supplying method and techniques are discussed in these paragraphs, which have been a part of past paper exams. Let me tell you, this specific diagram has been a part of exams like 6 to 8 times. You're going to see the same diagram. And they're going to ask you, why do we use aluminum, or why do we use a steel core, or why do we put up some insulating plastic right on top of this whole setting? Now you know. So moving on. So after solids, the question is, do liquids conduct electricity? If they do, what do we call them? So conductivity in liquids. We do not use the term conductor and insulator for liquids anymore. This is higher class. So we have proper terms. Electrolyte, if the liquid is capable of conducting electricity, and non-electrolyte, if the liquid is not capable of conducting electricity. Since insulators and conductors, let's take a few examples. Table 4.3 is filled with examples. Electrolytes include solutions of sulfuric acid, molten solution of any ionic compound, lead bromide is one of them, sodium chloride solution, hydrochloric acid, copper 2 chloride solution, sodium hydroxide solution. The point we're trying to make is that we can use molten salts, we can use their solutions, we can also use solutions of acids, salts, and alkalis. On the other hand, non-electrolytes, distilled or pure water is a non-electrolyte. So is alcohol, petrol, paraffin, molten sulfur, sugar solution. There are many non-electrolytes. Apart from them, the only metal that is liquid at room temperature, mercury, is also a very good electrolyte. But we usually call mercury a good conductor because it still falls under the category of metals. Even if it's liquid at room temperature, it still falls under the category of metals. Make sense?
Yes, sir.
Okay. The process is pretty simple. How do we check it whether they are electrical conductors? So we take the liquid, pour some of it in a beaker, put two graphite rods, which will be able to conduct electricity, connect them with either end of the battery. Negative goes to the negative end of battery, positive goes to the positive end of battery. And in between the way, on one side, we put up the ammeter, and on the other, we put up the bulb. As soon as the battery is turned on, if the bulb lights up, right, it's it means it's an electrolyte. It can conduct electricity. If the bulb does not light up, it means it's a non-electrolyte. It will not conduct electricity. That's how simple the experiment is. So once we start doing this, we need to understand that sometimes for some of these solutions, chemical changes start occurring as soon as we pass electricity through them. Sometimes the graphite rods get deposited with a metal or a solid. Sometimes bubbles start coming out of this solution in the form of effervescence. Sometimes we have a different liquid flowing with the liquid that is under test. That means there must be some chemical changes happening. So how do really these chemical changes happen? So we need to understand that, and that's how we describe it as electrolysis. Because ionic compounds, be it a salt, be it an acid, be it an alkali, be it in molten form, or be it in the form of solution in water, there starts a breakdown or a chemical change as soon as we pass electricity through it. So what we are going to do is that we're going to list all the kind of substances that act as electrolytes. So molten salts or molten ionic compounds is one category. And those same ionic compounds, when dissolved in water, which includes salts, which includes acids, which includes alkali, all of their solutions can also conduct electricity, which means ionic compounds can conduct electricity, be it their molten state or solution state. So we're going to do this as one type of electrolysis, and we're going to do all of these as the second type of electrolysis. So the molten electrolysis and solution electrolysis. But before we move any further, we need to clarify one thing. Now, since we have been doing this experiment, and I think you can easily see that we have the liquid, the rods that are conducting electricity connected to the battery. So the real question is, how is the electricity conducted in the outer part of the circuit? And how is electricity conducted in the inner part of the circuit? Means inside the liquid. Now, the outer part of the circuit is made up of metals, usually copper metal. And you know from metallic bonding that metal conducts electricity due to delocalized electrons, right? We have studied that as a part of metallic bonding. However, here, where we have the ionic compound, be it in molten form or it as a part of aqueous solution in water, this can actually conduct electricity because it has delocalized electrons, but because it has free to move ions. So their reason of conducting electricity and the reason of conduction of electricity in the outside circuit is totally different. And that is what is our very next point in the book. You're going to find a pink portion. It states that metallic conductivity is due to the flow of delocalized electrons. It's a property of metals, and only graphite is the only non-metal which can do that. However, some metallic alloys are also capable of conducting electricity. It takes place in solids as well as in liquids, and in case of metallic conductivity, no chemical change takes place. Electrolytic conductivity, conductivity inside the ionic compounds, be it molten form or solution form, is something different. Actually, in this case, electrons don't flow, ions flow. This is not a property of elements or metals, this is a property of ionic compounds. It takes place in liquids and solutions, it does not take place in solids. Ionic compounds are not conductors in their solid form. And lastly, in this case, chemical change do take place. And this starts decomposing, hence the name electrolysis. Now, if we are claiming that the ions flow, we should be able to prove it, that the ions move. And we prove it with a very colorful experiment on your right hand side. This colorful experiment is done with the help of a compound substance, copper 2 chromate 6, which is actually green in color. It is green in color due to two different ions, copper 2 ions and chromate ions. Copper 2 ions have this formula, and chromate ions, though that's actually not a part of O levels, but sometimes we do write the ions, have this formula and charge. Now, we do understand that we can conduct electricity by putting up graphite rods, one of them being cathode, one of them being anode, in a U-tube, U-shaped tube, not the YouTube, the famous YouTube, it's the U-shaped tube, I usually like to call it. When they are connected to battery and their positive and negative ends define the cathode and the anode, and when the electricity starts conducting, I hope you understand that cathode is connected to the negative end of the battery. So that means cathode is negatively charged. That's how it's capable of attracting copper ions. So instead of having all the green color over here, you'll see that the copper ions will start settling closer to this area. And that's why this area turns blue, since copper ions most of the time are blue in color. On the other hand, chromate ions, which are actually yellow in color, start getting accumulated towards this side. This side is anode, that's the plus side. Why? Because it's connected to the plus side of the battery. And since they are negatively charged, they get attracted towards the positive end. And that's how we are capable of proving that the ions move. That's why the green color was decomposed into two colors, blue and yellow. The color for copper and the color for chromate. This is a very colorful experiment. And right in front of your eyes, the green color breaks down into two different colors. And you can easily observe it. Now, this kind of experiment does prove to you that the ions are capable of moving and conducting the electricity at the same time. Make sense?
Yes, sir.
Now, from this simple experiment, we actually come to devise a few basic ground rules of electrolysis. What are those? In electrolysis, positive ions, which are usually metal ions, and sometimes they're going to be hydrogen ions, they can move towards the cathode. And that's why we call them cations. Negative ions on the other end, which are usually non-metal ions except for hydrogen, they move towards anodes. And that's why we have the name anions. Now, you need to understand something that cathode is negatively charged and cations are positively charged. That's why they are attracted. And anode is positively charged and anions are negatively charged. That's why they are attracted. I usually tend to ask my students to remember one set of lists along with their charges, and the exact opposite would be the other set of lists. Means if anions have a negative charge, anode must have positive. If cations have a positive charge, cathode must have negative. That's how the electrodes were able to track the specific ion. You get it?
Yes, sir.
Good. After we prove this, from here on onwards, the discussion about electrolysis gets pretty simple. Electrolysis is usually carried out in an equipment. It can be beaker, it can be tank. We usually call it electrolytic cell. Electrodes have their own names, anode, cathode, unit their signs connected to the battery ends, and because of those, the signs can be checked as per the battery's end. So we have this thing as electrolyte. So we know the terminology of electrolysis. If we know the terminology of electrolysis of molten compounds can be studied. But before I go with any kind of examples over here, I'm going to straight move to page number 108 on the book to where we have the whole electrolysis table. I love this electrolysis table, and I usually pick out this table to make sure that my students understand the electrolysis as a whole. Now we have an electrolyte, which we may state in the questions by its name or by its formula. Either way, you'd know that this is going to decompose into two parts. Since it's an ionic compound, it's made up of a metal and a non-metal, and you'll be amazed to see that every time the metals end up at cathode, and every time the non-metals end up at anode. That's how easy it is. I explain it in one more way. Whoever names come first will end up at cathode. Whoever names come after will end up at anode. In the similar way, whoever is written first in the formula is usually a metal and its name end up at cathode, like the all names do over here. And whoever has is written on the right hand side of the formula is usually a non-metal and the name is written over here. Make sense? So it's the easiest of tips. फॉर्मूला आएगा तो पहले जो लिखा जाता है वो कैथोड पे जाएगा, बाद में एनोड पे जाएगा. नाम आएगा तो जो पहले लिखा होता है वो कैथोड पे जाएगा और बाद वाला एनोड पे जाएगा. इट्स एज सिंपल एज दैट. आपको कैसे पता चलेगा आपने इसे कैथोड पे कैसे करना है? लेट्स क्लियर ऑल ऑफ दीज hideous arrows aside. It's pretty simple. लेड है, यहाँ पर 2 है, इसका चार्ज +2 है, इसके अंदर 2 ही इलेक्ट्रॉन्स ऐड होंगे तो ये बैलेंस होगा. Na का चार्ज +1 है तो 1 इलेक्ट्रॉन ऐड करें. K का +1 है, 1 इलेक्ट्रॉन ऐड करें. कॉपर का +2 है, 2 इलेक्ट्रॉन ऐड करें. अगर एल्यूमिनियम आता तो उसका +3 होता और हम 3 इलेक्ट्रॉन्स ऐड करते हैं. इट्स as easy as it is. On the other hand, anodes are slightly difficult क्योंकि diatomic ions बनाते हैं, diatomic molecules बनाते हैं, सॉरी. वैसे होना तो ये चाहिए कि एक ब्रोमाइड आयन जो है वो ब्रोमीन के एटम में कन्वर्ट हो जाए और एक इलेक्ट्रॉन दे दे, बट अनफॉर्चुनेटली ब्रोमीन एटम्स बहुत रिएक्टिव होते हैं और फौरन दूसरे एटम्स के साथ रिएक्ट करके ब्रोमीन का मॉलिक्यूल बना देते हैं। तो अनफॉर्चुनेटली ये मॉलिक्यूल साइन हमें यहाँ पर लिखना पड़ता है। जब हमें लिखना पड़ता है तो एक्चुअली हमें इस पूरी इक्वेशन को बैलेंस करना पड़ता है। सो वी राइट 2 ओवर हियर एंड वी कन्वर्ट दिस 1 into 2 as well. And then we don't need to write the separate equations. We can always write the overall equation. And you'll see all the overall equations are actually pretty similar to one another. Imagine these are all halogens, two halogen negative, halide negative, which I should call it, gives us the halogen in the form of diatomic molecule Br2Cl2I2 and gives away 2 electrons. That's how easy it is. So that means it's pretty simple. It's pretty simple and straightforward. So we have only 2 ions in the molten electrolytes. Remember, all of these are molten, all right? Molten means they have been melted into liquid by reaching their melting point, which means the temperature was really high when we were working with these. Molten also means that if they're going to ask this kind of electrolysis in exams, they're simply going to put this state symbol next to it, and they don't need to write the word molten. From liquid symbol, you'll automatically get the idea that the solid has been melted by reaching its melting point. Make sense?
जी सर।
Okay, if that makes sense, let's clear it up. Let's stop it right here. And let's do a little bit of practice. Now I am going to open up whiteboard and I am going to give you a couple of examples for molten substances. If you're ready with a pen and paper, it should be easier for you to tell me the answers. What you're supposed to do is tell me the product at cathode, the product name at anode, what's going to happen uh, in the reaction for cathode or reaction for anode. So I usually tend to make a small table like this. We're gonna start with electrolyte first, the product
सर
at cathode. Oh, I forgot to share the screen, my bad. Thank you for reminding. Okay, and the product at anode. And lastly, we sometimes write change to electrolyte, but really, if we are talking about molten solutions, change to electrolyte is that they are used up. We literally break them down into different into their constituent elements. Different by different, I mean the metal usually tends to go to the cathode, the non-metal usually tends to go to the anode. So that's what the difference is all about. Okay, so if I start with molten NaCl, which means NaCl as liquid, what are you going to get out of it? Now, I'm going to tell you a very simple tip to get this done. First of all, you need to convert them into proper ions with charges. We know since it's 1, 1, so it must be +1 and -1. Take one of them, the first one, to cathode. Since you know it's +1, you know it. You are supposed to add 1 electron to it, and there you go. Take the other one to the anode. Since the anions usually wind up as diatomic molecules, so we might need to balance the whole equation, 2 over here, 2 over here. That's how it's balanced. So it's pretty easy. We formed sodium in here because of this, and we formed chlorine in here. I'm going to erase these. Okay. So let me tell you, liquid, and even this one can turn in liquid, but you can write it as a solid. Liquid, since this was molten, but this time it's a gas. Change to electrolyte, consumed or used up. Because if we're going to use it up, that's how we are going to convert it or break it down into its constituent elements. So that's how it should be filled. Now, if you're clear with this one, I am pretty hopeful you will be able to solve a difficult one. So what would happen if I consider molten Al2O3? Go ahead. If you'd like to annotate it on my screen, you can do that too. I have already allowed it. And if you'd like to do it on a piece of paper and send me the picture, I can wait. Go ahead.
Aluminium. It would be
Aluminum.
aluminium
Good.
plus
Okay. So Al plus
three electrons,
3 electrons.
and then aluminium is formed,
Aluminum. Good. It would actually be Al3 plus. What about anode?
and then for the anode,
That's the
it
tricky
will
one.
be
Come on, the name of the product should be easy. Since there are only two ions in the structure, one cation,
it
one
will be
anion.
oxygen,
Oxygen. Perfect.
and
What else in the term of reaction? So what do? We literally start with this ion over here. So what's the anion? The negative ion is
-2,
O negative 2. Perfect. And that gives us what?
oxygen O2
O2. Very good.
plus
Plus
2 electrons.
2 electrons. But since there are two oxygen atoms, how are we going to balance it? Let's balance the
We're
rest of
going
the
to put
equation.
we're going to put 2 with the
The left
O2
of the
negative.
equation, right? Perfect. We are going to put this 2. There is one more step we need to take because of this 2. Because the entire equation changes when we start putting 2's. So what would happen to the number of electrons?
It would become 4 electrons
Perfect. It would
because
become 4 electrons instead of 2. That's it. And this side always stays as used up, so this shouldn't be a problem. So states liquid, liquid. Okay, this one's liquid. What about this one? What is oxygen in terms of state symbol? What is O2? Is it a solid? Is it a liquid? Or is it a gas?
it is a gas.
It is a gas. Perfect. Okay. We're going to quickly try and solve another one. That is Mg3 N2. Molten, of course, since this is in liquid form. So
It would become Mg2 plus and N3 negative.
N3 negative. Perfect. Okay, product at cathode.
It would be Mg2 plus plus 2 electrons will give us Mg.
Perfect. The name of the metal is
Magnesium.
good. Now the product at anode.
It would be N3 negative, means nitrogen, and it will give us N2 plus 3 electrons.
Okay. But since this is diatomic, are we going to balance the whole thing?
We are going to put
Again, the twos. This should be easy.
we're going to put 2 with the nitrogen.
Right. over here.
So it,
And what about number of electrons?
yes, it becomes 6.
Perfect. It's not 3 anymore, it's 6. And this is again used up. Do you get the point?
Yes, sir.
So that's what happens in case of molten. So you can always work it out. Okay,
Yes, sir.
good. All right. So that's about it. And I guess since it's time, we should stop right here, right?
Yes, sir.